if you know there's only going to be one constraint, you're going to win. So correspondingly, here, you're going to win. Here you're not because we're adding a function. Here you're going to win. Just straight away. Whereas here, because f is used twice, then you have to be suspicious and think about it.
Okay, so let's do this example. So unfortunately, we can't use Connor's handy tip because f is being used twice. So we need to do a bit more thinking. There are no plus signs, so we can't just check if a number is being added to a function. So we'll have to do a bit of thinking. So what can we see? So remember, and this is crucial, if you see something like this, a term, a term, and a term, this is being applied like this. So this is f applied to 0, and the whole lot applied to f.
Roger Hindley used to say, application associates to the left, rather as we all did in the 60s.
But you guys don't remember the 60s. In the 80s, did we? 90s, 2000s, didn't know.
Don't go there.
We all associated to New Labour. We didn't, did we? Anyway. Okay, so now that we know, so you have to remember this. If you don't remember this in numerous places, we're assuming you know this. Okay, so now what do we know? Well, actually, we've got the same thing Conor was saying before. Here, this f takes two inputs. The first is 0, and the second is f. So we know that f must have some type like this, and this 0 is a natural number. So f must have some type like this.
Nat rather than 0.
Oh, Jesus. Tried to do this too quickly. Nah, 0 is a natural number. But now, the type of f, sorry. So the first input is 0 for f, and then we'll have another input, which is the type of f. And then we'll have some output. Okay? But then this is the type of f. And it's also, that's the type of f. So we get the same situation we had before. We've got these constraints because we've got two uses, and we have to find a type, which is this type, which strictly contains itself. So that can't be done. Okay? Right, 6. What's that one? Lambda n.
Instant win.
Arrow lambda arrow f of n plus 2. Ah, brilliant. Okay, yes. So Connor's rule, f and n are only used once, so there's none of those constraints going on, so now we just need to check, are we using add right?
Yeah.
When we use add, do we give it numbers? Well, 2 is a number, what about n? Well, n can be a number, so that's typeable.
Oh.
Now, if you want to know what type it is, well, we just said this n must be a number because it's added to 2, so that must have type n. And this f, it's a function because it gets an input, and the input is a number because it's n plus 2. But then afterwards, we don't know anything else, so we can write sigma. So the output, the overall type, is the output of f, which is sigma. So this is like solving quadratic equations when you're 13, 14. You just do quite a few of them, and you get the hang of it. Which is why I gave you quite a few of them. Oh, can we have the last one. Right. Lambda f arrow. Lambda n arrow. Oh my God, did I write this down? Right, let's have a look. Oh, so we've got 3 uses of f, so we better be careful.
Think about it.
Right. So we know f is a function because it's been given an input there. It's also been given inputs here. One of the inputs is 2, so therefore we know the input of f must be a natural number. So we can fill that in. Now we know this n, it's also an input to f, and since the input of f is a natural number, we know this n must be a natural number. I don't know anything about the output of f yet. And then we're going to give something back. But now we need to check, so I've gathered all the information I can, and now I need to check, are there any constraints I'm not filling? So let's have a look. So the output of f must be a natural number, because it's going to be added.
Yes.
So I need to force this to be a natural number. And then this is the output of f. And then I just need to check all the constraints. Yeah. So here, f is being applied to 2, and it gives a natural number, so that's fine, and everything else works out.
Yes, so in particular, the result of this whole thing is a natural number, but that's perfectly okay to feed to f.
So that's typeable. So the overall story is to see if something's typable without writing out the big derivations. You're just looking through each of the variables, trying to see, is it a function? Or is it being used as the input of the function? Or is it the type of the output of the function? You collect up all that information, and slowly you get to a situation where everything types, or you find yourself with a constraint which you can't solve, in which case it doesn't type. Right.
Okay, I think I'm on next.
Okay. Any questions about that before we hand over to Connor? Nope. Good.
All right. So part B is about typed imp, and hopefully it wasn't all that difficult. If you remember that in the typed variant of imp, we were able, because we were no longer relying on the grammar to separate commands from numbers and from booleans, from integers and from booleans, we were able to let variables stand for anything, and I also threw in the back end of that document a way to add arrays to imp, and you could store anything you wanted in arrays, as long as everything in an array was all the same sort of thing. So we need to figure out, we can see that there are some variables in this expression. We need to figure out what types they end up with, and hopefully it's not terribly tricky. Can we see what type X is? Oh yeah, we can see it's given the value true and it's used as the condition in a while, so it's a bool. How about Y? It's an int.
Well, there it's an int, but
yes.
Can it be an int elsewhere? Maybe.
And then did I screw this up actually? Haha.
Z.
Yeah, so Z looks like it's supposed to be an int. This is excellent. Yes, so Z ought to be an int, except that here it looks like it's being used as a command.
Yes.
Which is wicked of me. That's what comes from doing these things at 5 o'clock in the morning.
Why you change the language?
Yeah, that means return.
Yeah. Oh, hang on. Yes. Z is being returned. It's outside the while loop. So that's fine, actually. So Z is an int, but it's being returned here. So we're computing, we're adding a bunch of stuff up to Z. And I'm trying to remember what the value of the whole expression is. But let's see what are we doing? We are doubling Y and counting the number of times we can double Y until and still stay under 9,999. So the correct answer is whatever power of 2 is 8,192, possibly plus 1 if there's an off by 1 error. So I think it's 13 or 14.
Yeah.
It's 14, I'm pretty sure. It's one of these things where the obvious thing to do if you're presented with a question like this in a lab is simply to translate this program into a language that you have conveniently the ability to run, and just run the program. If your translation is correct, you'll get the right answer without having to do any work. Without having to do any tedious arithmetic. So that's what I did. I think it was 14 from memory, but anyway, there was that. And then here is a large pile of massive assembly language, and we're trying to figure out which program gave rise, which source program gave rise to which lump of object code.
So, Connor, can I say something? Can you bring this down?
Yeah.
So, because this is the sort of thing we've been teaching you, it's the sort of thing that might turn up in the exam. So you might see something which looks a bit like this. And it's quite big, so at first reaction you might think, oh my god, how am I going to read every single line? And of course, we don't really want you to read every single line. What you should understand is the structure of how this works and properties of it, and that will allow you to answer the question.
Yes, so you need to be a detective. As we look at the source code, you can see that in 2 of our expressions we have while loops. In 3 of our expressions we have new. And then there are various things going on with the kinds of tests that happen here or the kind of assignment that happens there. So let's first of all go hunting for loops. You can see that what's going to happen with a loop tests a condition and then does a conditional jump to the loop body if that condition is true. So this looks like it's either part of an if or part of a loop. It jumps to 100. What happens at the end? We jump to 28, which is not even part of this program. So it's definitely not part of the loop. Actually, 28 is the same thing that the end of this thing falls into. So this ain't no while loop. How about this one? You can see that there's again a conditional, some sort of test happening here, and we end up at 52. If this were a loop body, this jump would take us back to the test. But it takes us to 42, which is after the test. So this ain't no while loop either. Okay, what happens here? Again, we've got this thing, there's a test, there's a conditional jump to 43. This might be a loop body. What happens at the end of it? We jump to 22, which takes us to some stuff which ends up at the test again. So this probably is a while loop. Then what happens here? Same sort of situation. We've got our test here jumping to something which might be a loop body. What happens at the end of it? We jump back to before the test. So that also looks like a while loop. We found our 2 while loops. We don't know which is which yet, but we certainly know that that the last 2 are A and B in some order.
So just to be utterly clear, you know, we've set this, we've taught you this stuff, we've set your questions in this style, so that's a style of question you might be examined on, so that's a style of reasoning you should be able to do. If it's a while loop, it's going to look like this structure.
Okay, so let's have a look at these 2 while loops. What's a good way, what's our strategy for telling them apart? Because these are quite similar programs. They both start with a new thing being set to 0 and then returning the final value of that thing. So that's not going to help us. But if we look at the 2 conditions in the while, or if we look carefully at the assignments being done, we should be able to figure out which one's which. This one's comparing y with 0. This one's comparing x with y. So this is comparing a variable and a constant. This is comparing 2 variables. So let's truck back up here at what is controlling this test. In both cases, we're comparing something from the stack with something in a register. But here, what's being put into the register before that? The constant 0. Whereas here, what's being put in the register is something made by looking at the stack at some offset from the base pointer. So that's where we keep variables, right? So here, we're definitely comparing 2 variables. Here, we're comparing a variable with constant 0. So I think we can tell which one's A, that's this one, and which one's B, that's that one. All right, so now all we have to do is figure out which of the other 2 are C or D. And there are various things going on. Again, we can look at these tests. Again, there's a comparison with 0, comparison with B. We can also see that C begins with a new. So if we spot anything like allocating some memory and sticking something new on the stack, then we might get somewhere. I mean, actually, this one, you can see, it's pretty much straight away, you know, it looks up a variable, puts it on the stack, looks up another variable, pops the stack, compares the two variables, happening straight away. Whereas what's going on here is much more shenanigans. You can see that
I spy 0.
well, there's a 0 here, yeah. It's also doing a calculation and then allocating space on the stack for the result of that calculation. You can see that all of a sudden in the rest of the program, we've got so the variables x and y have to correspond to these BP minus 2 and BP minus 1 things, and then all of a sudden we start filling around with BP plus 1, and that is, so the ones that are BP plus something are the ones that are allocated with new. So from all of these telltale signs, you know, what's contributing to this test? There's a comparison with 0 versus a comparison of 2 variables, and there's a calculation being done and the result stored on the stack, and then there's almost certainly by the time we finish, we're deallocating it. Actually, looking at the end of the where is that deallocation happening? It's happening somewhere. That's not it. That's just an ordinary pop. That finishes. Well, yeah, actually, that's the thing that is the allocated thing that we're ending up with. So that corresponds to returning the return A that comes from the new A. So indeed, D is 0 because it's not doing any allocation and it starts by comparing 2 variables. And number 1 is C because it has to be. Okay, so have we figured that out? Everybody happy with this piece of detective work? All right, we've got just under half an hour, and that was the end of that. I want to switch to showing you some kit, which don't worry about that lot. I'm just zooming in. This is the state of my Emacs at the moment. So.
Don't do this at home.
Yes. So, where does all this stuff live? If you haven't seen it already, it is worth finding your way. It's linked from the CS311 site to the repository for the massive machine. And there are lots of handy things in here. In particular, there's a document called compiling.pdf which explains how compilers work in this system. And there are 2 example compilers for our 2 favorite languages, imp.msv and there's also one for the Lambda calculus. And these are the compilers we've been talking about in lectures, but they're not just things written on a piece of paper in a lecture, they're real programs and they really work. So let's see them really working. What do I need? I need a terminal with big writing, otherwise we'll not see a thing. Remind me later. Can you read that? Or do I need to make the font bigger? I think I'll just make the font a bit bigger. Right. Oh, it's small m massive, of course. Yes, that's the joke. There's a whole lots of stuff in here. Right. So, somewhere in this directory, probably under source where it shouldn't be, there's an executable called massive. And if you run it without feeding it any input, it tells you what input it would like. Okay, so it's got a bunch of modes, and then you feed in a compiler, and then you feed in a program to compile with the compiler, and then stuff happens. So let's make stuff happen. So here's
That's a nice little grammar.
a program in imp. Imp in this compiler is extended with the ability to define functions. So this is the function which uses Euclid's algorithm, the world's oldest known program, to compute greatest common divisor of two numbers. So we're going to compute the greatest common divisor of 360 and 84, which I happen to know.
Isn't Pythagoras older than Euclid?
It's arguable whether Pythagoras' theorem constitutes a program.
Certainly would tell that.
So what's the greatest common divisor of 360 and 84? Well, I got it by multiplying 12 by 7 and 12 by something else. So it's 12. Greatest common divisor of 42 and 35, that's 7. 12 plus 7, 19 we're hoping for. So if we say source massive and we say compile with imp.msv, the program gcd.imp, so you pick a compiler and a program that you could feed to the compiler, then it spits out a big pile of massive assembly language, which of course is how I set all of these questions. You can just ask for a parse tree. So it reads the grammar and then it uses the grammar to parse the program, and that just spits out something that's fairly unintelligible that tells you which grammar and which production was used at that point. But the fun thing, of course, is to actually run the program. So we said we were expecting 19, and we know that that integer expressions leave their values in the first register. And guess what? The register set has 19 in the first register once we're done. Thank goodness for that. So, is it a fake? Well, let's find out. The obvious thing to do is to change the numbers so that this is, if I just make that 21 instead, then the greatest common divisor of 42 and 21 is 21. 21 plus 12 is 33, because it's 1 plus 2 twice. If we run it again, we get 33. So I'm not lying, it really is running this program.
2 tests and it's correct.
Yes, absolutely, absolutely. Okay, meanwhile, let's, I don't know, do I already have a function, a file called foo.lam? I don't, but I do, well, I do now. So let's do, I don't know, something like lambda f, lambda x, f of x, applied to itself, applied to lambda n, arrow n plus 1, applied to 7. Does anyone want to predict what the answer ought to be? Well, yeah.
11?
Correct. So this is the function that does twice. That does its first argument twice to its second argument. And this is, what we're doing is twice twice. That makes 4 times. And we're doing 4 times adding 1 to 7. So that should be 11. So if I do then this time in the rest register, which is where lambda terms leave their value, we end up with 11. Thank goodness for that. And because there's nothing that we like more than breaking stuff, let's see what happens. So, what are we expecting? Did you just, maybe I did that too quickly. What are we expecting when we run this program? Yeah, we're expecting nothing to happen, ever. And
by the way, just for your revision, remember that term. Anytime you want a term that runs forever, that's your term.
So, if we run bad.lam, it really does run forever.
Check the activity monitor. Can show his activity monitor and see it runs.
Yes, yes. Well, we can do more than that because we can actually do this. Oh, why did that not happen? That's weird. That ought to step. Why is it not stepping? Maybe there's something rotten in the state of Denmark. Better fix that before John gets his hands on it. I just got a text from John Levine kind of shouting for this program. Yes, you can also, by the way, ask it to step through. So here was our GCD example earlier, where there's our 360 and there's our 84, and there's some more stuff elsewhere. So you can step through what's going on. It's always, so you see IP is 2, and here's the code from 2. So you can really watch it go. Stuff appearing on the stack. I mean, it's not exactly an ideal spectator sport, but you can see here we are comparing 360 with 84. And I just sort of round a while loop. We've subtracted 84 from 360, and we've done it again, and again, and again, and now we have to start subtracting 24 from 84, which happens gradually. 30 down to 36, down to 12, and then we subtract 12 from 24, now we've got 2 12s, and that means 12 is the answer to our first calculation, and the stack pointer drops back out to the outside. I'll stop there, because it's not all that exciting, but you can entertain yourself by writing programs and watching them go. You can also fiddle with the compiler if you like. Let's have a look at the compiler, which I showed you bits of in class on Tuesday. I wonder, do we have any bits of paper left? It would be good if there was some paper. Yeah, here's paper. Right, so how does it work? You need to do 3 sorts of thing to write a compiler in this language. you need to give the grammar of the programs you're going to compile. And we've given you a grammar notation. I adjusted it the other day so that it's easier to say things like application associates to the left. The idea is that you can attach an optional level to a non-terminal symbol, and then if you could also have one of these things that looks a bit like a non-terminal symbol, but it's got a number in it instead, and that just makes a demand that the level be at most this number. So what this is saying is, because application is a level 3 construct, and it's we've got a level 2 here, that means application is allowed here, because 3 is bigger than 2. Whereas here, on the right, application is not allowed unless you put it in parentheses. Yeah? See what's going on here? So, so here, this is saying applications are allowed without parentheses in the function position, but not in the argument position. And here we're saying, because this has a low number, 1, it's lower than 2, it's lower than 4, that if you want to make a function or an argument in an application, if you want to make that a lambda, again, you need parentheses. So that's how we resolve the ambiguity in the syntax. Then there's this thing which we call the compile directive, and that's where you say what's going on at the top level. Here I'm saying the whole program is a term, and for sake of argument I'm calling it source. And then I have to explain how to get my hands on the entry point to the program. So I say, well, compile source with this exit point, and this is a panic instruction, and then give back the starting point. So this is just how you glue the thing to the outside world. Say, here's how you compile the whole program, and here's where to start executing. And then you write a bunch of compilation schemes. In this case, we just have one. It's designed to look like the grammar, and it works like the grammar. So you say, first of all, you declare how you're going to compile each sort of non-terminal symbol. We're going to say, we're going to compile terms. The extra information apart from the term itself we're going to be given is an accessor, namely the exit point, and we're going to give back an accessor, namely the entry point. And then we write down a bunch of compilation rules, which are following the productions of the term grammar, and they're in the same order of the term grammar, one rule per production. So we have to say how to compile variables, how to compile applications, how to compile all the other stuff, how to compile lambdas, and so on. If you were, for example, to be asked to compile, I don't know, lambda x arrow x, then you could start figuring that out. The compilation rule tells you how to generate code for that. It tells us that there's going to be a thing called start. It's got FP is assigned to body. We're building a closure. FP plus 1 is given by RE, and RE gets the pointer to the closure, and FP goes up by 2 because we've allocated that memory now, and then we end up at our end point. But that's not the whole of the story, because there's a thing called body, and that's made by compiling the variable x, and there's a thing called done, which looks like SP, popping the stack, and then it's going to the return address. So all we have to do is fill in body. Body is made with the compilation rule for a variable, and it was handed, what was it handed as the entry point, or the exit point? It was handed done. Okay, so so what do? We say, well, and its starting point was going to be body. So starting from here, we can copy out the code. We just put x into the symbol table, so its index will be 0. And then we go in a straight line to this coder thing, and that's going to be, I didn't actually need to make that a separate lump of code. 0, so we, is that 0? Well, it will be, in fact. If so, jump to car, otherwise work your way along the environment. Oh, I do need a code pointer there, because I go to coder. And at car, I say RE is given by taking the thing up the environment at that point, and then jumping to the place that was the designated exit point, which when we, because it was called by the lambda, that's done. So the compilation rules just tell you exactly how to generate code. When you get a compilation subtask, you can just you switch to following the rules for that subterm. So we compile lambda x arrow x by first of all following the rule for lambda, and then by following the rule for a variable. And what you need to do is, essentially copy out the code blocks, and whenever you get a compilation subtask, you can substitute in the code that's generated for that. You might have to rename the labels so that you don't get any clashes, but just systematically running the compiler for, at least for small programs, is not so tricky. So a good thing to try doing if you've got your hands on the massive technology is perhaps to try taking an imp program or a lamb program, compile it by hand, and then see whether you get the same code as the actual compiler. Anyway, I think it's probably time to pop the metaphorical stack, and I think, well, thank goodness that's done. It's been a bit seat of the pants. We haven't really known, how much we're going to be able to do. Thank you for keeping us from going too fast most of the time. But we've managed to work all the way from the sort of the syntax of programming languages to thinking how they go, to thinking about how we check whether they make sense, to figuring out how to turn them into code for a vaguely realistic machine. I mean, the massive machine is kind of a lot like x86 machines, except massive. X86 machines can run out of memory and stuff like that. Yeah, and of course, this lambda calculus compiler just casually just spends more and more memory building closures and environments as if there was no end of the stuff, because in the massive machine there is no end of the stuff. whereas in a real implementation, you need to be a bit more careful about recycling memory that isn't really being used for anything anymore. And that's the exciting world of garbage collection, which caught on eventually. I guess I'll finish. Sadly, I don't happen to have the video, but there was a meeting in Germany some years ago where the guy who headed the team at Sun Microsystems that invented Java, a guy called John Gage, he gave a talk about like inventing Java, and there was a question and answer session at the end where he was accused of stealing modular 3. Basically, said, why didn't you just use modular 3? He was, he said, modular 3 with C's syntax. And to defend himself from this accusation, he listed all of the other sources Java had stolen from. And the killer line was, we stole from ML, the original typed functional language. We stole from ML, but not enough. So there was Java had a static type system, had a garbage collector, all of this sort of stuff. So yeah, there's programming languages evolve slowly. There's an awful lot of fantastic intellectual theft going on. Those of us who are in the programming language design business, our attitude to intellectual security is to turn the stereo up, wind the window down, leave the keys on the passenger seat, and generally point. Because one thing is for sure, these days it's extremely difficult to take over the world by inventing a new programming language. But what you can do is invent prototype languages with some nifty features and then try and get those features stolen. And that's our game. We're pretty good at it, actually. And yeah, so that's the kind of fun we have in this business. And it's just wonderful that programming languages as a discipline never stay still. But that means you need the tools to keep up with and understand the kinds of new gadgets that people keep putting into programming languages. And hopefully the sort of transferable skills from this class will be, when somebody puts some kind of new gadget into a programming language, you watch it, resumable exceptions, they're coming your way. And you can begin to think through, what does this mean for the type system? What does this mean for the dynamic semantics? What's going on? If we have given you better equipment to think through what's going on with the features of programming languages, we've done our job and hopefully given you a useful tool to take into the workplace or wherever you end up. Stop there?
Yep.
Thanks,
Thank you very much.
We have